Hello, welcome to my presentation video on photovoltaic installation part 3. In this video, I'm going to talk about PV installation architectures. A PV array is made up of a number of modules in series or parallel corresponding to the input characteristics of the inverter. However, since these modules are interconnected, the array is very sensitive to shade or differences in terms of the direction faced. By following a few simple cabling rules, supply can be optimized and any operating problems may be avoided. When installing a PV array on a roof, panels need to face in different directions. It is essential to assemble at least one string per direction and ensure each string is facing in just one direction to ensure optimized supply. Each string must be connected to a specific inverter. If this instruction is not observed, the array will not be damaged by supply will be reduced, thus increasing the time needed for a return on investment. Besides the risk of destruction of shaded modules within a PV array due to the hotspot phenomenon, for which manufacturers have devised solutions, research conducted by France's National Institute for Solar Energy suggests that shading of 10% of the surface area of a string may cause more than a 30% reduction in output. It is therefore important to eliminate direct shading. However, in many cases, this is difficult due to trees, chimney, neighboring wall, pylon, etc. If a PV array includes several strings, if possible, shaded modules should be included in a single string. Otherwise, a technology should be chosen that responds better to diffuse light than direct light. When connecting components, the first precaution to take is to avoid loops in the cabling within strings. Even though direct lighting strikes on arrays are relatively rare, currents induced by lighting are much more common, and these currents are particularly destructive where there are large areas of looping. The image on the right shows how to improve an array including a large loop. PV array with a single string of modules is the simplest configuration. It is used for small PV arrays with peak power of up to 3 kW peak, depending on the modules deployed. In most cases, it is used for residential PV operations. Modules are connected in series, supplying direct current of between 200 and 500 VDC in this instance. Optimal efficiency is obtained from the inverter within this voltage range. A single DC line is fed through the inverter. The PV array can be isolated from the inverter by means of a load break switch near the inverter. PV arrays with several module strings in parallel are mainly deployed on buildings or in small PV power plants on the ground and are used for PV installations of up to 30 strings in parallel with power output of 100 kW peak. The strings are paralleled in a PV string combiner box. This box includes the safety devices required for paralleling the strings and appliances used to measure the string's current. A single DC cable connects these boxes to the inverter. The PV array can be isolated from the inverter by means a load break switch near the inverter. On this slide, we can see a diagram with a multi-string PV array with one inverter. Another configuration is PV array with several strings divided into several groups. When power levels exceeds 50 or 100 kilowatt, photovoltaic arrays are split into subgroups to make it easier to connect the various components. Strings are paralleled on two levels. Strings in each subgroup are paralleled in subgroup PV string combiner boxes. These boxes are fitted with safety devices, the necessary measuring equipment and monitoring devices. The outputs of these boxes are paralleled in a PV array combiner box near the inverter. This box is also fitted with the required safety devices, as well as the measuring and monitoring equipment necessary for paralleling the subgroups. The array can be isolated from the inverter using a load block switch, which may or may not be fitted in the PV array box. On this slide, we can see a diagram showing a photovoltaic array consisting of several groups. An alternate solution to the DC system is to closely link the inverter to the PV module. In that case, the PV module becomes an AC power source. This solution, called PV AC module or string inverter, is common for small installations but can be used also for larger systems. In that case, all the paralleling and wiring is done in AC. General rules for AC system apply. On this slide, we can see a diagram with the architecture based on PV AC modules. The installation type is a factor which should not be neglected since in countries, including France, the purchase price for power supplied is dependent on this. Along with shading, it should be taken into account when choosing a module. There are three installation types: building integrated, partially integrated, and ground-based. Building integrated PV installation type fulfills a dual role: energy supply and roof waterproofing, shading, etc. Partially integrated PV is the simplest assembly to install and most importantly does not alter the water resistance of a roof. However, its major drawback is that in France, operators cannot charge the highest rate for it. The installation type is most commonly used in Germany and Switzerland. Ground-based PV installation type is used for power supply plants covering large areas. Again, in France, it is not eligible for the highest purchase price. Let's have a look at the electrical equipment selection for grid-connected PV systems less than or equal to 10 kW. Where a 5 kW grid-connected single-phase inverter is installed with the maximum open circuit voltage less than or equal to 600 volts, in this design with one or two strings, no string protection is required. A PV main switch is necessary. When the inverter is indoors An additional remote controlled switch at the DC cable entry point is recommended for emergency services. Now, let's have a look at the electrical equipment selection for grid-connected PV systems in the range from 10 to 100 kW. In the design were a single MPPT grid-connected inverter up to 60 kW with the maximum open circuit up to 1000 volts and one string combiner box is installed. The reverse current protection is required as the design has more than two strings. Multi-single MPPT grid-connected inverters, typically in 6 times 5 kW to 20 times 5 kW configuration, are used for residential buildings as this design can be duplicated as often as necessary. In that case, the DC system is very simple and the AC system very similar to usual AC systems. Now let's have a look at the electrical equipment selection for grid-connected PV systems in the range from 150 to 500 kW. The design where a single MPPT inverter up to 500 kW is installed with more than two string combiner boxes is very similar to the three-phase inverter with one string combiner box, except that it has more arrays which requires array cable protection. When a PV system is installed for grid feeding, utility that operates the grid will provide requirements for protection, disconnection, and metering functions. Each utility may have specific requirements according to local habits and grid specificity. As a general rules, the following functions are required: energy meters, disconnecting device, overcurrent and earth fault protection according to earthing system, and anti-islanding protection. As there is a physical connection between the two installations, the self-consumption of PV production comes with specific installation rules and architecture requirements. Electric installations with local PV generation for self-consumption could be designed to operate only grid-connected or grid-connected and islanded. In only grid-connected mode, in case of blackout at the electrical network side, the electrical installation is no longer supplied by the local generation. Current PV systems used for self-consumption operate mainly in this mode. In grid-connected and islanded mode, the electrical installation operates connected to the grid, but can also operate in an off-grid mode, supplying the totality of the loads or part of them with the local energy sources. Today, PV installations cannot assure the operation of the electrical installation in off-grid mode standalone, as the produced PV energy is volatile, predictable, but unplannable, and with limited control capabilities. To assure an off-grid operation, PV installation must be associated with another major and stable source such as storage or generator. Also, the operation of the electrical installation in both grid-connected and island mode is much more complex and requires a dedicated control. This kind of operation is rare, especially in countries where the electrical grid is stable and blackouts are abnormal. We come to the end of this presentation. Thanks for watching.